All right, welcome to session 8 for our relation of science of physics to theology. So let's begin with the word of prayer. Dear Lord, again, we come here to consider the world that you have made, the way that it works, and how you have revealed yourself to us through it. We are so grateful that you give us the opportunity to understand things and that you help us then to use them to glorify your work in every way. We do ask you to be with us now in Jesus' name. Amen. Okay. I have a verse for us this morning that is pretty cogent to what we're going to talk about. 2 Peter 3:8. But do not ignore this one fact, beloved, that with the Lord 1 day is like 1,000 years, and 1,000 years are like 1 day. We're going to be talking about the special theory of relativity, and that will involve the concept of time and the relativity of time, which is an interesting topic all by itself. The theory of special relativity explains why the speed of light is constant. There are some really strange ideas that come out here for some of us, and we're going to find that it leads to new limits on knowledge. And there are some applications in philosophy that shouldn't be made, which we'll talk about also. Now, in reviewing what we've done before, the basis of all this, of course, is that God's creation is both knowable and stable, that what he reveals to us is not only true, but it doesn't change and doesn't contradict itself. So what we learn from Scripture, what we learn from science can't contradict each other because God is not contradictory. We studied classical mechanics and thermodynamics, and we found that their rules of conservation of energy and increase in entropy are valid over a wide range of experience. And we also learned that the laws of classical physics, Newton's mechanics and Maxwell's electromagnetics and all this together, which we thought at the end of the 19th century was a theory of everything, we found out that they don't work when you go to extremes of size and speed. And there are rules then that are called quantum mechanics that will explain some of the discrepancies that come up in classical physics. And that was our subject last week. We found out that quantum mechanics requires that you have to use statistics in understanding these things. And we get something called an uncertainty principle out of quantum mechanics. And both the statistical view and uncertainty principle have their philosophical and theological implications. And that was where we ended last time. And I guess I maybe didn't even ask if you had any questions last time. I'm sure you might have some, and if you want to ask them now about the previous sessions before we start the new thing, I will try to address them.
You did ask
last. And nobody spoke up. Okay. And you haven't thought of anything since then. Very good. Okay, well, now, what is time? I'll bet you think you know what it is, right? Oh, it's now 7 minutes after 11. Well, that's not what we mean by time. Okay, that's what time it is, but that's not what time is. Our intuitive feelings of time are somewhat unreliable. I'll give you an example. When I'm enjoying something very much, the time just goes by so fast. But have you ever sat in a dentist chair and noticed how slow time passes? There is a relativity there in our own understanding of time in an intuitive sense. But in physics, time is essentially an ordering relationship, saying that one thing comes, then the next, then the next, then the next. This sequence is what defines time. The fact that we have this ordering and that it can't be reversed is what's called the causality principle. If you have a cause and it's an effect, You have the cause first and then the effect. You can't turn that around and have the effect followed by the cause. All right? If you're going to measure time, you need something that repeats itself on a regular basis. Just like if we want to measure distance, we take a stick, maybe a yardstick, and we put it down again and again. Because it's of a regular size, we get a feeling for how big something is. Well, the same way for time. To get a feeling of how long a period of time has passed, we need something that changes in a regular way to use to measure that. And of course, the measurement of time historically has had many different ways of doing it. In early days, maybe they burn a candle down that burned at a certain rate, and that would tell you how the hours passed. Or you might have a pendulum clock that ticks off the seconds for you. You can have an hourglass with sand running down to give you time. And of course, this is all pretty well related to the rotation of the earth for the concept of a day and dividing the day into subdivisions of hours and minutes and seconds and so on. Now, modern time standards use atomic vibrations to be the thing that occurs regularly. And you know, the only way you can really test these is to compare two of them to see if they agree. It's interesting. How do you know when a clock is absolutely right? And the answer is you don't. You use one as a convenient way of measuring things, and you would hope if you have more than one that they agree with each other. Okay? Now, the problems of modern physics. Aristotle's, here's one of the things we've talked about before, but Aristotle's system was replaced by Newton's system. Each one of them was mistaken as being absolute truth in their day, which led to later problems. Quantum mechanics now explains experiments where these extremely small things don't follow Newton's laws, like atoms or atomic particles. They follow the laws of quantum mechanics, which essentially meld into Newton's laws when the size of the object gets bigger. Quantum mechanics doesn't fix all the problems with Newton's laws that come up in modern physics. There's still the problem of things that move at high rates of speed, and Newton's laws don't seem to work there. Now, where this first comes up is with light. How light propagates brings along investigations that when you try to explain them in the old ways, they use strange ideas. One was a shrinking ruler, that when a ruler moves parallel to its length, it shrinks. Oh, okay, well that will explain some of the strange things that you otherwise see, but it's kind of an ad hoc explanation. We'll get more into that later. But Einstein had a better way to do it. His special theory of relativity solves the problem of the speed of light. Now, what's the problem of the speed of light? I haven't introduced that, and maybe I should. I will here in a little bit. But we'll just say that Einstein's theory takes care of the problem, and it has some really important consequences. Now, this special theory of relativity has lots of experimental verification. It's not something that is just far out, wild idea, but it has a lot of experimental justification for it. And it agrees with Newton's laws at lower speeds. So again, just like quantum mechanics agreed with Newton's laws for larger objects, so Einstein's theory agrees with Newton's laws for things that are moving at reasonably slow speeds. This special theory of relativity, as we will see after we get done talking about it otherwise, we'll see that it puts some more limits to knowledge and that there have been misapplications of this in philosophy. Okay, now, here's where the problem begins. It's with light. Newtonian mechanics showed that waves, we talked about wave motion, like waves on water, waves in the sound, waves are on something. There's some kind of a medium that has a wave in it, right? So when the idea of electromagnetic waves came along, the scientists said, there's got to be something for them to be waves in. Well, these light waves can go through a vacuum. So whatever this stuff is, it has to even exist in a vacuum. And so they gave the name of ether to it. This was an old idea from way back in the Greeks that there was such stuff. But anyhow, this ether has to be everywhere, permeating everything so that electromagnetic waves can propagate. Now, once you have come up with the idea that there's such a thing as ether, then you start to have these questions. Well, I wonder how the earth is related to the ether. Does the earth move through the ether, or does the ether move with the earth when it moves? And how would we be able to tell? And for that, we have to do experiments on light. And we'll talk about Michelson-Morley's experiment in a little bit, but first off, let me just give you an idea of what we're talking about in general. If I had a truck and I put a water tank on the back of it, and I started making waves in my water tank and they move along, and then I get in the truck and start driving it off, and I'm standing here beside it and I see those waves going by, guess what? The waves would be going by faster for me than they would be for somebody standing in the truck. In other words, we would see the addition of the truck's velocity to the wave's velocity. All right, in sound waves, the same kind of thing happens, and I'm sure we're all familiar with this. It's called a Doppler shift. But if somebody with a loud, noisy car is coming toward you and goes by you, it goes, yeah! As he goes by, the pitch drops. Well, the reason, because when he's coming towards you, the sound waves he's putting out at a given rate, as he gets closer, those sound waves are closer and closer together when they get to you, so it sounds like they're a higher frequency. But when he goes away from you, he's moving away from you, so they're getting farther apart, and it's a lower frequency. Okay. Now, what about light? Well, the experiments that have been done show that it doesn't make any difference how fast the emitter of the light is going. It always looks like it's going the same speed when it gets to us. Now, the original motivation behind this was this bit about the ether. So these people named Michelson and his cohort Morley came up with a very sensitive experiment that could detect very small changes in speed of light in different directions. And he could find out that you measure the speed of light in this direction and in direction perpendicular to it, and they were always the same. But he thought, now, let's rotate it. And if we rotate it, if the Earth is moving through the ether, then because of that effect, like on the truck, you know, it's the ether now we're talking about. The ether's moving, so we should add the speed of the ether to the speed of light, and we should see a difference. Well, he found out there's never any difference. The speed of light's always coming out the same, no matter what direction I look. So now you've got a real problem. Either there's something strange about light, or there's something strange about the ether that it's stuck to the Earth, okay? And somehow now the Earth is the center of the universe again, and ether is stuck to it. Okay, well, this was a problem. Well, along comes then a man named Lorentz, and Lorentz, it's called Lorentz Fitzgerald Transformation. This business about shrinking the ruler, we can explain why the speed of light doesn't seem to change if the way we're measuring it changes. And if the ruler we're measuring it with, or measuring wavelengths with, shrinks when it's moving, then it'll make it look like the speed of light stays the same. Even though it's not really, it's just a ruler that's changed. Okay, well, that's kind of a strange way to look at things. But he was able to come up with mathematics then that would explain what we saw. Okay, I already talked about the idea of having of that, but now let's get back to coordinate systems, because here's how we can try to explain it a little bit. There's always been the problem of what happens when you're moving to compare to when you're not moving. If we have what's called an inertial reference frame, that's like right here, we're stationary. We call this an inertial frame because in an inertial frame, an object at rest stays at rest, remember? And an object that's moving continues to move in a constant velocity in a straight line unless it's acted on by a force. Any system where that's true is called an inertial frame. And you can have more than one inertial frame by having one move at a constant velocity compared to the other. So I'm drawing out here a coordinate system again with axes x, y, and z, and another one, x prime, y prime, and z prime. And this x prime, y prime, z prime is the one on the back of the truck, okay? And it's moving at a speed u in the z direction. And now if I want to measure something in this moving coordinate system, and I put it at a point that I call x prime, y prime, z prime, and I've got a clock in here, and the clock is reading time t prime, there gives me a coordinate of something. But from the viewpoint over here, that coordinate, assuming that these two were together when time was 0, what we're going to find is the x and the y's are the same, but the z's change because the z over here keeps getting bigger by this product of the velocity and the time. So we have these formulas that connect the coordinates in the two systems, and we assume that the clocks are the same. T is equal to t prime. They were synchronized when they were together, and they're equally good clocks, okay? Well, anyhow, that's called the Galilean Transformation, and it works with Newton's laws. Newton's laws appear the same form in the moving system as they did in the stationary system. The only difference is you add to the velocity in one compared to the other. And that's just common sense, okay? It's kind of a common sense transformation. The problem with that is that would not work if you had a source of light over here and observing it here, because you ought to see the velocity of light change then. Then it doesn't. So how are we going to explain that? Well, we explain it by changing to a different transformation called the Lorentz transformation, which looks a little bit the same and a little bit different. First off, the x's stay the same and the y's stay the same, but the z's don't stay the same. The z, instead of being z prime plus ut, we have to have a thing in the denominator, the square root of 1 minus u squared over c squared. And likewise, the clocks don't stay the same. Whoa, that's a tricky one. But the clock over here and the clock over here, the times are related. Hey, if it's 1 o'clock here, it's 1 o'clock plus uz over c squared divided by 1 minus u squared over c squared. The times change too. All right, well, that's the mathematics of it. And that mathematics keeps the speed of light constant. We haven't shown that yet, but if you went through it, it would explain why the speed of light stays constant independent of the motion of the observer and the emitter. Now, if we look at those formulas, we see that c is the speed of light, which is this very big number. Remember the speed of light? 186,000 miles per second. 3 times 10 to the 8th meters per second, or that turns out to be 670 million miles per hour, if you like miles per hour. It's pretty fast. And because it's so fast, if this u is reasonable, I mean, hey, you don't want to go over the speed limit of 70 miles an hour, we put 70 divided by 670 million and square it and see what you get for a number. It's so close to 0 that your calculator ain't even going to show it. It's just going to be 1, and it's going to be like that was just 1. And the net result, you've got the u over c squared over here too. These are going to disappear, and it's going to just look like the original Galilean transformation that works with Newton's laws. So whenever the speed is reasonably low, there's no problem. It's only when the speed gets to an appreciable fraction of the speed of light that you notice this effect. And that's why it's not part of our common sense, because in our common sense, we don't ever have anything moving that fast. The first time I ever ran into a case where I had to worry about that was in an electrical engineering class where we were looking at a cathode ray tube, like an old-fashioned TV tube, where there's a stream of electrons, comes off of one end and flies to the other. And you can get those electrons going up almost to the speed of light. So you have to start doing it this way to get the right answers to your problems. Well, moving on from there, that looked kind of complicated, but Einstein was able to derive that transformation from just 2 simple postulates. And here they are. The principle of relativity, which says All natural laws have the same form in all inertial frames of reference. By the way, Newton's system and the Galilean Transformation obeyed that postulate also. We're saying that if F equals ma in one, F equals ma in the other. Okay? But Einstein added a second one. Real simple. The speed of light is constant. The same in all coordinate systems. Those two things alone will enable him to get that messy looking mathematical formula. And we will investigate how to do it. Now, I hesitate to do this because when I was an undergraduate, I was always just snowed by these so-called thought experiments. It wasn't until I got to graduate school and learned to do the higher math that it became simple. But I'm going to try to snow you with it anyhow. And there are a couple of preliminaries that we have to do. Now, the first preliminary is we wanted to show, and I'm going to go back to the previous page. We want to show that the x and x prime are the same. That is, links don't change in directions perpendicular to motion. And here's how you do it. I have a green pen and a red pen, and they're the same length when I put them next to each other. Now, if I'm moving this one by fast, and I look as they go by, if this one's longer, it would be obvious, right? But from the viewpoint of the person who was riding on this one, it's like this one went by. And when it went by, it would also have to be longer if moving makes them longer, but they can't both be longer, so they have to be the same. So they don't change. So there's no change in links perpendicular to the direction of motion. Okay, that's item number one that we have to get out of the way. Now the second item we have to get away has to do with two clocks. I got two clocks. And they're both in the same plane. I got my wristwatch here, and I've got a clock here in my cell phone. And they don't quite keep together. After an hour or two, there's a second discrepancy between them, that the wristwatch gains a second in an hour. Okay, maybe needs a little work on it. Okay, gains a second in an hour. If that's the case, suppose I start moving them real fast. They're still going to gain a second in an hour relative to each other. It wouldn't make any sense if they didn't. Because if they did, then I would know I was moving. And part of the whole theory is you can't tell which one's moving. There's no real distinction from the viewpoint of the person who's riding along in what we think is moving versus me being here and thinking I'm stationary. The person that I think is moving thinks he's stationary and we're moving. See that kind of a relative way of looking at things? If I have a perfectly good, smooth, moving laboratory and I'm in it, I think I'm stationary and everybody else is moving. Have you ever sat on a train in the station and the one next to you starts to move and you get the feeling you're moving? That's the kind of thing I'm talking about. If you've never had that happen, take a train ride sometime.
Or in a parking lot.
Yeah.
The other car moves and you're stationary.
Yeah.
And it's scary.
Yeah, right, okay. So that's the idea, is you really think you are stationary and everything else is moving. Well, the other guy has the same viewpoint. He thinks he's stationary and you're moving. So that's why if my two clocks run different when I'm stationary, they've got to run different the same way when I'm moving, or otherwise I would have a way to detect absolute motion. And we're assuming that is not possible. So the only reason I say all this is it doesn't make any difference what kind of a clock I use for the rest of my discussion. Any clock will work. So I'm going to use a very peculiar kind of a clock. It's called the light pulse clock. And the light pulse clock, we're going to have a vertical distance, which remember now is not going to change when it moves. And we're going to put a mirror on one end of it and a flash bulb at the other. We're going to flash the flash bulb and it's going to go up and come down again. And then we'll flash again and that. And that's a light pulse clock. And the round trip time is the clock tick. So the round trip time for the stationary clock is going to be the distance it moves times divided by the speed of light. Well, the distance it moves going up and down is 2L. So 2L divided by C is the clock tick time of the stationary clock. All right? Over here, we have the clock that's moving. From our viewpoint, it's moving. And in that frame of reference, we see that the pulse of light didn't just go up and down again. It had to go at an angle in order to get back to the mirror. And so, from the mirror back to here. So the distance it went was 2d. So 2d divided by c, the speed of light, is its clock tick. Okay. But d is longer than L. So this clock tick is going to be longer than this one. Now, the expression of how they're related is mathematics to derive it, but we know enough here to do it now. If I wanted to go ahead and actually work out the algebra for you, we'd have to use the Pythagorean theorem. D squared is equal to L squared plus 1/2 U delta T prime squared, because U delta T prime is how far it moves in that time interval. So if you want to really do the algebra, I know you don't, but we'll do it anyhow. What we have here is D squared equals L squared plus 1/2 U delta T prime squared. That's the Pythagorean theorem. The other one is, the other equation is delta T prime is equal to 2D over C. And the equation delta T is equal to 2L over C. And so now we have to do the algebra with that, and that part I will skip, okay? But when you finish doing the algebra, this is the answer you get. Delta T equals square root of 1 minus U squared over C squared delta T prime. All right, that factor, 1 minus U squared over C squared, is the relativistic factor, and it's sometimes given a symbol gamma. But you'll note that it's almost exactly 1 if U is any reasonably slow speed. Like as we said, maybe U was 60 miles an hour and C is 670 million miles an hour, then that's pretty much just 1. And the clocks run at the same rate. But if the speed at which we're traveling should turn out to be as big as the square root of 3 over 2 times the speed of light. And why did I pick that number? Well, again, back to the algebra for a minute. Suppose U was equal to 0.833 C. That's about square root of 3 over 2 C. So that U squared is therefore 3/4 C. All right. And what does that mean? U squared is 3/4 C squared. So U over C is equal to square root of 3 over 2, which is at 0.833. Okay, so what's the point? Well, the point is U squared over C squared, U squared divided by C squared, 1 minus that is equal to 1 minus 3/4, which is equal to 1/4. And the square root of that then, 1 minus U squared over C squared, is equal to 1/2. So what we find is that delta T is equal to 1/2 delta T prime. So if you're going that fast, you would find that your clock was running at half the speed of the stationary person. Okay, well, that would be quite a change. You could probably notice that, all right? Slowed down by a factor of 1/2. Let's move on another way. The factor in the length, this business about shrinking rulers, all you got to do to show that is flip this light pulse clock over on its side. And I don't know that I have a picture for that. I think I don't. So I'll have to draw the picture. I don't want to lose this one altogether. What I just want to say is if you're going at that speed of 0.833 times the speed of light, clocks run at a factor of 2 different, because we'll come back to that in a minute. But the light pulse clock laid on its side looks like this. Here's the flash bulb and here's the mirror, and the distance is L. Okay? The delta T, remember over here, the delta T that we get from the clock this time is just the ratio of 2L over C if it's stationary. But if it's moving, the clock when it's now moving, pulse to here and back, this distance is not L, it's L prime. And the speed at which it's going gives me delta T prime equals 2L prime over C. And so from that, we get the ratio of L to L prime is like the ratio of delta T over delta T prime. So it's this same factor that shrinks the length in that direction. Okay, well, that's an interesting little excursion into the easy way to get Einstein's formulas. The hard way, or maybe it is easy, is when you have advanced math, you can do some stuff that shows that you get those formulas too. All right, this leads us to something called the twin paradox. Now, let's suppose we've got a pair of identical twins. Imagine Wild and his identical twin brother, whatever. Well, then we'll let them be a little older. We'll let them be old enough they can be astronauts. One of them is going to get on a rocket, and he's going to take off, and he's going to go at a speed of 0.833 times the speed of light. That means his clock is running half as fast as the clock of the twin brother who stayed home. Now remember that all clocks work the same way, run at the same speed. So my biological clock is affected the same way as my wristwatch. Consequently, while I'm traveling at this high speed, I'm not aging very much. So suppose he goes out that way, and I think he's gone a long time. He comes back, he's been gone 10 years. I'm 10 years older. He's only 5 years older. Oh, that's strange, really strange, right? Now, paradox. What's the paradox? Well, the paradox is, from the viewpoint of the twin, I'm sitting here in my rocket ship, and this guy back home is flying away from me very fast at 0.833 times the speed of light. So he must be aging slower by a factor of 2. So when we get back together, I'm going to be the old one, and he's going to be the young one. Whoops, they can't both be true. What's wrong there? What's wrong is we forgot something. Einstein's theory of special relativity only applies in inertial reference frames, meaning ones that are moving at a constant speed. But that rocket ship couldn't be moving at a constant speed, or it could never have started off and turned around and come back. There's an acceleration that happens there. And during that acceleration time, things don't work quite the same way as they do when they're going at a steady speed. Well, you've got to do the next one called Einstein's general theory of relativity to understand that one. And according to that, and I haven't done it myself, but according to what I read, is it solves the paradox. And it turns out that the one who stayed home is really the one who's older, the one who wasn't accelerated. But it's a paradox in the special theory of relativity until you realize the special theory of relativity does not apply because you have an acceleration present. Okay. Moving on, this is what everybody thinks about if you say physics, right? They say, oh, E equals mc squared. Einstein, mass and energy. If you have a mass of a kilogram multiplied by 3 times 10 to the 8th meters per second quantity squared then gives you the amount of energy in joules contained in that kilogram. And it's a very big number because C is a very big number. Okay, that follows from something else that you have to work in mechanics now and explain how Newton's laws have to be changed to work in this relativistic system so that F equals ma is not just F equals ma anymore. It's, as we said earlier, it's F equals the time derivative of the momentum, and momentum is the product of the mass and the velocity, and the mass goes up when velocity goes up according to this formula with this same funny thing in the denominator, 1 minus u squared over c squared. So you start out with a mass m sub 0 called the rest mass. That's how much you have when it's stationary. When it's moving, the mass is increased by that factor. Again, you got to be moving very, very fast for it to make much difference. If you were going at 8/10 the speed of light, the mass would be doubled. Okay? But doubling the mass, how did you get it doubled? You had to accelerate it. You had to do force, which was work, so you put energy into it. And through all that, Einstein comes out and shows that the energy associated with the mass is equal to the mass times the speed of light squared. Now, that's okay. What else does it say? Well, if you look at that formula, it tells me that nothing can go faster than the speed of light, because what would happen if u equaled c? Denominator goes 0. Anybody ever tried fooling with that and on a calculator? Try divide by 0 and see what you get. And you get an error message. You can't divide by 0. But as it gets smaller and smaller and smaller, this gets bigger and bigger and bigger without limit. Okay? It's another way of saying you can't do it. You can't accelerate something to the speed of light because of this formula. Well, what about light? Doesn't light go at the speed of light? How about photons? Remember, in quantum mechanics, light can be understood as being little particles called photons, which are moving at the speed of c. Well, it turns out they're okay because they have 0 for the numerator. The m0, they have no rest mass. They can never be at rest. They're always moving at the speed of light. So you got 0 over 0, which is not a usable number. In math, you call it indeterminate form as you approach that. But at any rate, massless particles go at the speed of light. Particles with mass can never go that fast. If they went faster than the speed of light, what would happen? Anybody know what happens to the square root of the negative number? Imaginary number. Why is it called imaginary? Well, because it seemed pretty strange. But in mathematics, it's okay to have imaginary numbers, but imaginary masses, I'm not so sure what that would mean. Okay, so we probably think that doesn't happen. Although there was a time when some people thought there were such things as particles they called tachyons that would go faster than the speed of light. Nobody ever found one, and the theory is a little bit dubious. And if they did, they would be strange, okay? Photons don't have a rest mass, but they have a relativistic mass because they have an energy. Remember that a photon has an energy that's equal to Planck's constant times the frequency. So if that's the energy, if you divide the energy by the speed of light squared, you get the mass. So therefore, the mass of a photon is m equals hf over c squared. Wow, so they have mass after all, because they're moving at the speed of light. They have a relativistic mass. Can we prove that? Well, sort of. If you watch light going by the edge of the sun in an eclipse, you see that it bends as if it's being attracted to the sun, like it had a mass of that value. So that's one of the confirmations of this theory. Okay? That it can be affected by gravity. Well, how's that for one morning's lesson? The philosophical implications now. If the speed of light is finite, that puts a limit on knowledge. I can't know what you're doing back there in that corner until the time has passed equal to that distance divided by the speed of light. That's a pretty short time, so it's not much of a limitation. But in astronomy, it's a big limitation. I can't know what's happening on Jupiter until probably 20 minutes after it happens because of the time that it takes the light to get here from there. And if I'm looking at an image of a star that is 8 light years away, then it takes 8 years for the light to get here. So what I'm seeing is what the star looked like 8 years ago. If I'm one of these guys using the new James Webb telescope and I'm looking at something that is 12 billion light years away, then I'm seeing what it looked like 12 billion years ago, not what it looks like today. There's a limit on our knowledge in this inherent finiteness of the speed of light. It also, in the same way, puts a limit on how fast I can interact with something, because you essentially have to have a round trip to interact with something. And so a round trip at the speed of light is the fastest you can interact with something. Seems like pretty trivial for everyday experience, but when we start looking at astronomical events, it's not so trivial. Like, how would I send people on a trip to another star? Because I can't go to the speed of light. I could get as close to it as I could possibly get there, but I can't get there quite. So it's going to take at least as long as it takes light to get there. And so a round trip from here to a star that was 8 light years away would take at least 16 years. It'd take something longer than that. So that'd be a long time to wait to get the information back. There's a lot of other problems there too, but that is the ultimate limit. Well, the theory of relativity, the philosophers want to say, okay, we've learned now that things are relative, so maybe morals are relative and everything else is relative, and that just does not follow, because the speed of light is a constant. It is not relative. It's an absolute. Okay. Now, here's a problem. Quantum mechanics. We didn't go into all these details of quantum mechanics, but there's some stuff that is called entanglement that you may have seen about for communications, or things like quantum computers, all these new ideas. These have all come about fairly recent years. The entanglement didn't. Einstein didn't like the idea because it sounds like it's action at a distance that's instantaneous. It violates this constancy of the speed of light. So there's a problem of reconciling quantum mechanics and the theory of relativity, okay? They're still not unified even today. I will say, however, that the special theory of relativity and electrodynamics have been unified in a thing called quantum electrodynamics, and that's a pretty well understood discipline. But the total unification of what we'll learn as the general theory of relativity and quantum mechanics is still an open problem. People would like to figure out how to do it, because we aren't back yet to the what should I say, place where we were at the end of the 19th century of a theory of everything. We're still missing some pieces. Now, I said a similar problem exists in theology, exclamation point. Theologian, tell me what that problem would be. I'm guessing that most theologians have never even thought of this. The limitation on knowledge. How can God know what's happening here and also what's happening on Alpha Centauri at the same time? Well, okay, but you didn't answer the real question, is how does that fit with the theory of relativity? Yes. It's a theological problem that's not been thought about that much because most theologians don't study the theory of relativity. And it is a conceptual problem. And I would answer it by saying theory of relativity is not the absolute truth. Let's not get into that little catch again. That's what's caused all the problems in the past, is saying one of these scientific theories is absolute truth and therefore such and such can't be. Well, okay, turns out none of these theories are ever the absolute truth as far as we know, so we'll leave that as an open question. Yeah, it's well confirmed by experiment, but that doesn't make it the absolute truth. Okay. Well, next time, here we go again. Except this time, it's called general relativity. Is what do you do when there's an acceleration and not just a uniform motion? This has implications in cosmology more than anywhere else because it really doesn't have any effects on a small scale. And when we're talking about that, we're doing extrapolation because we're applying things where we can't go out and do an experiment to verify them. So that's sort of where we're going to be in the next class. Again, if you need to get links to things, you can send me an email and I'll send them to you. Most of you, I've already sent all the links that have been here before. And you can download the materials. This link I've also sent, since you wouldn't want to type all that in by hand. That's where I have this material on a Dropbox where you can get these slides, you can get the PDF file, the handout, and even more importantly, you can get a PDF file of the original lectures I gave on this subject back in 1972. And they are, in a lot of ways, better than what I'm saying here. I went back and looked at some of them yesterday and found a mistake and corrected it. But that's the way things go. Okay, what are the questions for this morning? Okay, a couple from Harry.
When you were talking about the twin brother.
Yes, the twin brother question.
That one went out at
Yes. One going 8.33 speed of light.
so as he's going away, he is aging up.
Yes.
But wouldn't it, as he comes back, wouldn't he be aging faster? So that when he got back, he'd
Okay, the question is, if he's aging less on the way out, wouldn't he be aging more on the way back and therefore be the same age when he got back? And the answer to that is not during the part of the time he's going at a uniform speed. He'd be aging slower while he's going at that uniform speed because it didn't care which direction you were going in the formula. The formula for the clock tick does not depend on the direction. U squared is in there and the squaring gets rid of the sign of the way you're going. So the change has to be during the deceleration, acceleration times. Well, that's a good question.
Second question is relative to your verse that you quoted. I think it said something about 1,000 years ago. Like one day and one day is like 1,000 years.
Yeah. And what about that?
There seems to be something in that quote that relates to speed. So high that it's infinitesimal speed. And at infinitesimal speed would have an effect on that.
Okay, you were saying that the quote, and I'm repeating this, Harry, because otherwise they can't hear it. You can't be heard on the mic. The quote from Peter, of a day is 1,000 years, and 1,000 years is a day in God's sight. And you were saying, I'm not quite sure I follow the question.
Well, putting 1,000 years into a day implies incredibly fast.
1,000 years into a day would be incredibly fast. Think about that one a little bit. In order to get the clock that's going slower, yeah, you're right. He'd have to be going really fast so that he only saw a day go by while you saw 1,000 years go by. Right.
That implies something about
Yes.
something going incredibly fast has an effect on the mass.
Oh, yes. The mass also goes up while it's going so fast. But that's from our viewpoint. From the person who's going that fast, they don't think their mass has gone up. And they think your mass has gone up because they think you're going away very fast from them. So it's a reciprocal thing. And really, though, the quote has more to do, is more relevant to what's the difference between enjoying a good conversation and sitting in a dentist chair. From the standpoint of in other words, it's the concept that God can comprehend long periods of time just as well as we could comprehend short ones, I think. That's what we're saying. So in a sense, maybe the quote was not real relevant, except that there is a certain relativity to our understanding of time. But thank you for the question. Anybody else?
I say that quote would imply that God is traveling very fast. That we're just sitting here.
Yeah. The comment was that the quote would imply that God was going very fast versus our sitting still. Well, perhaps, but I think the other side of it was reciprocal. 1,000 years is a day, or a day is 1,000 years, which would make us going very fast. So probably stretching things a little bit too much for that.
I just take it to philosophy.
Yeah. Taking things to their logical conclusion sometimes gets one in trouble. Okay.
As I figured out philosophy.
Oh, we have a philosopher. She's taking philosophy. Good for you. None of this came up in it, right? None of these things came up in your philosophy class?
Not really, no, but there have been a lot of really interesting philosophers who take the logical conclusions of what we heard.
Yeah. Philosophers taking things to the logical conclusion of absurdity. Yeah. All right. Okay, well, listen, thanks very much. I'm sorry that I probably should just take the mic off and go hand it to you when you're commenting. Okay, well, if there is nothing else to say, oh yeah, Wayne, back. Uh, Well, actually, I haven't. It sounds intriguing. The comment, which I'm not even sure I can repeat it all, but some physicist has written a book in which he has tried to reconcile the age of the Earth as 4 billion years versus 6,000 years or whatever would come from a Usher's chronology by saying that one was being measured in a time frame at the origin of the Big Bang and the other in a local time frame or something like that. I think is the gist of what you're saying, but I'd have to see the book to see exactly how his argument works. Of course, that's always a dangerous place to go because Big Bang theory and what happened at the beginning is not something well understood. Okay, Gerald Schroeder. Uh-huh. Okay. Yeah, right. Okay, I haven't seen them, but that'd be interesting to look at. Okay. Gerald Schroeder written 3 books on reconciling God and science. Okay, well, very good. Thank you. Anything else? All right, well, let's have our closing prayer. Dear Lord, we thank you again for giving us challenges of understanding of your world. We know that it's not always simple, but we know that it is in your will, that you have made things in the way they are for our benefit. And we thank you for allowing us to understand some of it, to use that. And we pray that we will use it in a way that is to your glory. We now thank you for all things and ask for your blessing in all that we do. In Jesus' name, amen.